I apologize for that. Anyway, so we're going to examine some large language models and how they perform with visual reasoning. So the outline of the talk is to explain what we mean by multimodality. We'll show you some examples. This has become a popular field really within the last 3 to 4 years, but the basic premise is you will present an image, or you will present a description of an image, and from the language and vision model side, you will either create it or describe it. So there's a number of reasoning tasks you could imagine if you were doing, say, a logic test. Complete these 4 sequences. That would be a typical kind of task you would do here. And then we're going to try and propose some large language models, which will be referenced here as LLM, to evaluate and compare them. So that's an important field today, just figuring out how do you know a model is getting better or how do you know it's getting worse. I will say, just to give a lead ahead, that some of our findings is that despite the fact that, I think the world has been playing with these large language models for at least the last year, there remains some sensitivity to the way you construct the prompt. And that, in some sense, makes it more fragile. You have to establish the context of a question, or you maybe want to set parameters for how you want it answered. So essentially, we're going to address some of that by showing a series of image dialogues. And most of those will present a somewhat ambiguous image, and then slowly, using the chat memory, we're going to try and uncover what's really going on in the image. Another main finding with large language models, of course, is they typically lack a lot of context for what we would call world knowledge. So this might be, water flows downhill. If you just spider the internet and collect all of the text about which way water flows, a lot of that text will actually be jokes or humor in which water flows uphill. And so the fact that it doesn't know that and a 3-year-old child knows that still remains an open problem. I think they're getting much better at that. And of course, there's a whole field of using, historically, 30, 40 years, of using games and puzzles and logic and strategy over time to exercise what we describe as the current state of the art for artificial intelligence, whether that's chess or Go or something else. Those are important aspects of the AI history, and we'll explore some of that with this new toy, this new large language model. So ultimately, we will give 47 tests of visual language and present that almost as a data set or a new evaluation criteria. So what are multi-models per se? For our purposes, it's really just computers that see and speak or understand language. So vision and speech or language text, the ability to read and understand, have really been the core of, you might say, what establishes humans as a distinct species, particularly because of language. But also in AI terms, you gain so much advantage if you can see the world, navigate the world, and then essentially catalog the world using language. But ultimately, we're going to present it as an experiment. There's really no theory. I'll put it this way. The theory lags the experience. It's somewhat similar to biology in the sense you have to do a lot of trials, and eventually, if you see a pattern yourself, you can propose a kind of theory to wrap that. Also, we're unlikely to discover the limits of these without directly probing the model. So this is my personal opinion, but for example, really in the beginning of 2023, there was a big push in the AI community to freeze all models. And I think you have to admit an assumption of that is that there's some theory by which you could evaluate those models without actually touching them. And I think that's remains a big challenge. So it does remain a sort of limited by what you can probe it with. And so essentially the internet and academic research has begun to catalog the failure and successes and define its capabilities. So this is sort of a short version of how you construct a multimodal model in kind of a cartoon way. this is really showing the key aspect of how a model, an AI model, is either deconstructing an image or proposing text generation. And essentially, it's predicting the next word. So you can imagine as if, in some cases, you don't know the destination, but you're essentially laying the track to the railroad as you do it. Sorry, it's a little distracting. I want to freeze that. Anyway, for this, I'll go back. For this purposes, combining a language. So in a traditional English language, predicting next word is that cat sat on the mat, and you would essentially begin a sentence and then complete the thought. In an image, a number of people found that these transformers, which are really, if you want to think about them broadly, they're essentially a way to compress a tremendous amount of knowledge and then query it. So if you think of it as a massive zip function of the internet, and your inference step or your prediction step ultimately becomes a very nice way to unpack that zip file in a lossy way. But essentially, one aspect is just like a sentence, you can deconstruct an image. And so in this case, we have a train and a conductor, and we're going to cut it into 4 pieces, and then we're going to ask the model to analyze each piece. And we have a train, a conductor, a track, and what I'll call a ticket. And then essentially we ask the model, given those 4 elements, construct a description. The interesting thing that sets transformers apart, and this was a nice breakthrough, was as your context window gets large, so think of a book, and you're predicting next sequences, you want to maintain the context of characters from chapter to chapter, and that becomes enormously computationally expensive. So one of the features of transformers is to assign what is sometimes called attention or weights. So if you're looking at this image, the key aspect, the key take-home is the train and the conductor. The track is an important part, but you can infer that from here, and the ticket also is an important part. So the bottom half of this image, you want to build a neural network, or essentially a weight biased equation that emphasizes really the top half of that image. So let's begin kind of with the way we approached probing this. We will take various tasks like summarize this section, or complete this thought, or translate this piece of Spanish into English. Those are typical language tasks, and we will map that language understanding to visual tasks. And really the interesting part, and I think the thing that's really got people's attention, is you used to, up to a year ago, you would submit, each time you would submit a question to the model or the oracle, you would essentially have to reestablish the context of the question. So you couldn't say, Bill went to the store, where is he? Those 2 sentences, the he would not reference Bill unless there was some memory. And that memory becomes GPU expensive, meaning it takes a lot of graphical processing units to store that memory, and you have to be very clever about the length of that context window. Some interesting practical examples of what I would call image-related aptitude is part identification. So here you see a picture of an image of a car engine, and we're going to ask various questions about that. But part identification, whether you're assembling an IKEA piece of furniture or anything else, part identification is pretty important. Games, puzzles, and logic, I mentioned before, is a keystone for artificial intelligence. And then when we talk about how would you build world knowledge, I think there is a model out there that you would just sit the model in front of YouTube and hit go. And, because of its computational power, it would eventually understand enough of the image and the sequencing of time to, for example, look at Niagara Falls or some other waterfall in the world and establish the fact that water will flow downhill just by observation. So this is kind of the way we constructed the paper. We provide an image and we ask, what is this? We catalog the response. In this case, this is from Google Bard, which is a large language model open to vision. And it gives a very, very specific answer. It seems to recognize some components of this image. It's a V8 engine. It's a Ford Mustang Shelby. And it gives some alternatives here. Now, the next sort of a civilian question would be, can you help me find the oil? And if you zoom in on this, it's somewhere down here. And this brings out an important aspect of the language model when you think about how it's cutting this image up. It typically doesn't want to memorize the order of the way it was cut up. So it can be somewhat vague about exactly where in the image the object is, but it seems to infer it's in the top, located on the top of the engine, meaning it's not underneath the car, and near the front of the car. So somewhere here, it's round with a red or yellow label that says oil. So that's a pretty reasonable computer answer. I think I pause here just to sort of let it soak in how hard that would be to solve if you were constructing a rule-based car repair. Again, this is sometimes called zero-shot learning, meaning the model just knows because it's looked at enough of these pictures on the internet, and you're not essentially training this per se on car engines. So this is the list that OpenAI put out of things not to do with a vision model. In other words, we recognize it does some things well, like image part identification was pretty good, but don't try and do these things. So obviously medical imagery, life and death situations, it's probably unsuitable. There's a big field of the training data is very biased toward English. And so a lot of people, and as a consequence, a lot of the instructions you can give it, like don't act like a toxic person, as a precursor for AI safety, it's very, very good at following those instructions in English, but people have begun to exploit it in terms of taking a less obscure, more obscure language, crafting a toxic response, and then asking it to translate it, and some of its safety features will go down. It particularly mentions non-Latin alphabets like Japanese or Korean. Big text can confuse it. It's like if I take 50, if you go to the internet and take 50 pictures of dogs, because humans are taking it, you'll typically see the dog in the center of the image. That's a big clue about human bias, but we also have a characteristic size. We like to see text, and enlarged text can create some problems. Just like humans in optical illusion, rotation of the image can make it difficult for people to understand it. And then finally, the sort of visual elements, fine detail, I mentioned already, kind of the notion of it may not try and preserve the order of the patches in the image, particularly when you get to graphs or text where colors or styles, you think about, I want to give it a scientific paper and ask it to reverse engineer the data behind the chart. That would be a typical question, and that can be still challenging. Spatial localization, so we'll get to some of this, but if you go back to the AI story of a machine playing chess, spatial localization, where's my king, where's my queen, those can still be pretty challenging. And I think because of that cartoon I showed earlier, when you patch up the image into 64 or 16 pieces in a chess game, it may not preserve the relative order. It's really trying to find the key elements and weight those. And it serves a positive purpose in terms of reducing the model size and compressing the image, but it's not very good when you go to the fine task that humans do in spatial localization. Different sort of bizarre ways of looking at image, a typical 2D image versus a panoramic or fisheye are good tricks. It does not really try and mine the metadata or the size of the image. So this is somewhat important, but not a little bit technical. But the idea is, if I really wanted to use a large language model to label an image, so let's say a dog next to a cat, I would need the specific pixel relationships. And it doesn't typically do very well to say that's a 416 pixel by 416 pixel image, and the dog is at 100, 100, 100. So in some sense, that's missing that element of its learning. Because it's a language model, people have always made fun of the fact you used to be able to ask 2 + 2, and because it had read some joke on Reddit, it would say 2 + 2 = 5, and that would show how badly trained the model was. People have gotten much better at counting, but you have to understand, you have a calculator for that, and computers are very, very good at that, better than humans. But the idea that a language model would be the way you would approach addition or multiplication is probably not true. And finally, CAPTCHAs it's actually pretty good at, and we'll show you an example of that. But for safety reasons, I am not a robot, or the ability that you identify yourself as a human has in many cases been hindered by the model designers. So let's essentially go to some experiments and introduce the idea of BARD versus GPT. We don't know much about the inner workings of these models. They're both closed source. They're enormously effective. They're enormously expensive to run. But the question we're going to do is we're going to take a picture of this hand. It looks like a left hand. And we're going to estimate the age based on this hand. So the way we're going to do this is BARD will be the left side. That will be the answer that Google gives. On the right side will be OpenAI or Microsoft. And so Google essentially, BARD answers the man's age is mid-30s to early 40s. I don't know how it knows that's a man. It does say it's well-developed and has some wrinkles, could be in his early 20s. Knuckles are prominent. I guess that's how it tries to find it's a man. Not yet in his 50s. That's pretty good. It's specific enough. You could design a test for it. GPT, at least in the first instance, will say, I cannot help that with you to release these vision models. There was a lot of care taken to avoid facial recognition. I would say that's 99% of the controversy involved in releasing vision models to the wild is someone takes a high school picture and someone stalks someone based on how it recognizes that person and tracks them through multiple other images. So it still is a very troubling thing, but they're quite happy, for example, analyzing a car engine. All right, so back to our car engine idea. Let's get a little more specific with our BARD. As we showed earlier, it gives a very good answer. And actually here you can see the oil, where it shows it, and it says it has a red or yellow label. It may be guessing that. I haven't mentioned a lot about the what's sometimes called hallucination, which means you can think of it as a people pleaser, meaning it has instructions to help humans. And in the absence of some information, it will, in many cases, begin to make up stuff, and you have to accept that. And it typically will say that from the outset of when you first log on to ChatGPT, it will say, don't trust it. It's interesting, in GPT's case, it seems to be much less specific. It just says it's a car engine. It's definitely a compartment. It doesn't even try to find the oil. So again, it's a one-off case, but you can see some challenges there. All right, this is a classic, constructive visual reasoning question. Here's a picture of a refrigerator. Give me a recipe. So comes late in the day, you open a refrigerator, you say, this is what I've got. I can't go to the store. So Google BARD understands enough of what's going on in this refrigerator, and it does propose a chicken stir fry with rice, and then it goes down and gives instructions. The interesting part about this, and we developed this much more in the paper, but this is where you can really have a dialogue with the model. And that's the fascinating thing, because you can, for example, ask, I have a dog and I want a leftover. So size the meal for one human and one animal. Or you can say, I have certain dietary restrictions, and it will it will shift the standard recipe you might read in a book. And GPT, also from OpenAI, will similarly give some sort of sandwich with a side salad. It's not clear as you probe this image as a human exactly where it's coming up with some of these, but it is very, very good at recipes, and it's very good at following the instructions to refine it, particularly in terms of ingredients or doing the math of being a cook. This is a kind of, you might imagine running into this on a visual logic or an IQ test. This image is actually from a meme that transfers on the internet, and it's typically found on something like Facebook. And depending on how the human interprets this image, we have a snake. He may have been, the man may have been chopping this tree down. We have a lion and some alligators, and he's in a bad way. And so the proposal, I think, to humans is save your man. And you can propose this to a machine learning model and ask it to solve the problem. The BARD initially says clearly the man is in a dangerous situation, and then it does give it. It typically will give in the first sentence like a call for help. It's not clear that that's part of the rules, or there are no real rules, but can he get outside it? Can he ask for assistance? And where is this guy? Is this the guy chopping down the tree? But it gives use a sturdy branch that supports your weight, keep your body. So they're more concerned about him falling down into the alligators. But I guess the idea is to somehow climb up, don't jump from the tree, whatever happens. In a much longer scenario, ChatGPT says you could wait, you can swing, you can distract, you can climb, or you can call for help, like a whistle or something. Again, pretty good. And I kind of don't want to underestimate the challenges of constructing this from any sort of rule-based, even symbolic AI. All right, I mentioned that CAPTCHAs, or prove you're a human, is a typical example, typically in visual settings, of a Turing test. These designs are essentially trying to beat the handwriting recognition algorithms by their original design, and they've sort of been vulnerable really since 2015. Interestingly enough, this advanced image process typically will sometimes try, sometimes refuse, sometimes it seems to be editing itself. But you can ask BARD, at least when we did this, I think this was probably July, that version of the model would actually break this CAPTCHA. So 2B827, clearly they've done some obfuscation of both the pixels and the lettering. Interestingly, so if you look into how BARD is doing this, there may be some optical character recognition. Sometimes people use the open source tool called Tesseract. But my guess is BARD is using some of its own AI underneath it. It's not simple OCR. OpenAI will make the guess. It also gets it wrong. It's 8827, so it reads an extra 8 in here, so it would actually fail that. And subsequent volumes will actually dispute the fact that it don't give me more CAPTCHAs. This is a classic vision-only problem. In other words, there's a huge infrastructure on the internet. If you're looking at security cameras or whatever, just tell me what's in this image. Is it a man? Is it, or even some situational reasoning? And so we're going to present an overhead image. Most of the image classifiers are more from eye level of humans, but this is a satellite image of an aircraft carrier. We asked BARD. It says it's a large gray aircraft carrier, very specific. It seems to be taken from a satellite and shows the carrier in great detail. And again, this is all zero shot. It has no pre-training based on satellites. So that's quite remarkable. And again, GPT, and we'll get to, I'm sort of loading the deck a little bit in favor of BARD, but we'll get to some GPT-specific examples later. Again, very, very good in recognizing the satellite perspective. It's top down. It gets a little more vague here. It's cargo, container, might be military, hard to determine. So again, if you want to continue the dialogue, for example, ask what would a runway be doing on a cargo ship, you could probably flesh it out. But anyway, it is remarkable zero shot learning. An important aspect of any machine interrogation is emotion. We kind of assume that humans have that the biology has a kind of monopoly on emotion. And so there are lots of, sorry, these are low resolution images, but there's lots of psychology experiments where images of different emotional tone are presented to humans. And after many, many humans view those images, you can get a kind of consensus view. So this is a panel that we presented to both BARD and GPT, and we're looking for image sentiment, evaluate the emotion based on these collective images. So you have some sort of classic human triggers like snakes, you have some warfare, you have some insects, you have some medical sort of scares here in terms of surgery. So a human probably will, the actual technical version of this in terms of psychology is these are angry images. There's typically a very narrow spectrum, so it's not all that specific, but sad, depressed, happy, serene, peaceful. So interestingly, Bard is very bad at this sort of montage. It gives it a serene. I would challenge someone, unless you're a doctor, maybe to see this as serene. GPT-4 will say correctly anger, and the actual human score is called OASIS, or Open Effective Standardized Image Set, and it ranks all these images in the category of anger. So this will eventually, I think, become a more prominent part of these models, because particularly, the simplest is toxic versus non-toxic, or mature versus capable, or appropriate for children. Those kind of cases take a lot of human content moderation now. And this, if you could nail this image sentiment, it's an enormous field for application. Okay, now let's try and probe. And again, you have to kind of view yourself like you're a doctor diagnosing symptoms. You don't actually see the disease yet. You're just asking questions. So it is well known in the field that computer vision models do not see like we see. So, for example, the way we're trained has a lot of sort of psychological elements of edge detection. So we tend to be very shape sensitive. If you think of the way a computer model is built, it's looking at a central pixel and 9 pixels around it. So it tends to be biased more towards texture. So people have figured out elaborate tests for this, but we want to add a third axis to this, which is, because we're dealing with a vision language fusion, we also want to look at the label sensitivity. So if I present you with a cat and it has a label of a dog, which one is the model going to choose? So here's the example that people may be familiar with. If you look at if you're sensitive to texture, you can recognize this as an elephant skin. It's wrinkled. And you can recognize this as a cat with very high confidence, but you wrap the cat in the elephant skin, and typically a texture shape Q conflict is what is called. It will see the dominant aspect the machine sees is the texture, so it will say that's still an elephant. We presented, because it's a language vision model, we presented with a cat overlaid with the word elephant, and both these models nail it. They will say GPT-4, Bard will say it's a cat laying next to a sign that says elephant. So it's clearly has some, in some sense, compartmentalization of its choices. And GPT-4 Vision also will say it depicts a cat with elephant. It may be humorous, it may be mistaken. So it tries to reconcile the Q conflict, but it is an interesting example. The reverse image is more biased to, the reverse test case is more biased to language, in the sense that all these models recognize ASCII text. So you can go to the old teletype version of ASCII art, and this is an elephant and ABC, all the characters on a typewriter, and both models will fail to recognize that as an elephant, which does tell you something. Obviously, it's incredibly scale sensitive when it analyzes that, but if you're looking in this kind of block here, it just looks like gibberish. All right, here's a big class that both models fail on, and it's somewhat close to the heart of people who work in AI, and that is anything to do with games or puzzles. This is really, because they're easy to score, they have enormous attraction for people designing tests. So checkers, Go, Rubik's Cube, Tic Tac Toe, Othello, Reversa, or the old favorite of chess. So you can present the status of any game. So if you're solving the Rubik's Cube, you can solve this in one move, one twist, but ask the model to predict the next move. And, it's, for all fairness to these models, the way they chop these images up, a lot of the memory is lost. But in this case, if you're playing Go, you're building a sort of territorial gain, and this is your next move. So a good answer is the machine would go from look at this and put a stone here. So just for purposes of this, they all fail. I mean, you can actually ask it to reconstruct the game board, like a simple one like Tic Tac Toe. Here's the image. What do you see? It will answer with absolute confidence and give you the wrong answer. So clearly, this is somewhat embedded in a lot of troublesome aspects of large language models, how they hallucinate, how they are people pleasers by design, and also how the order sequence may be a bit fuzzy. There is some early success with crosswords, and visual logic is improving, and we show some examples of that in the paper. So now you've gone through enough examples. It's a little bit of a hodgepodge, but you can begin to design common categories of things based on applications you want this model to do. And so a lot of those edge cases would involve the Q conflict. So shape versus texture, or the language doesn't match the image, or you're describing something I can't complete. So typography is if you're thinking of this as knobs on the machine, there's all kinds of variations in typography, foreign, spelling variations, synonyms. So if I say cat or feline, do I get different imagery? Out of vocabulary. So you can talk about these sort of fictional worlds that are created, like Lord of the Rings, where you might have names that wouldn't obviously be recognized as common names. Conceptual challenges, so fonts designed within images, text embedded in an image. So this becomes, interestingly enough, this has become a popular attack vector. Because it's seen a lot of imagery on the internet from things like email or embedded imagery, that's typically wrapped to ASCII. So the image isn't binary anymore, it's base 64. And so you can get it to analyze all kinds of toxic images if you just encode it in base 64. So again, a lot of these are kind of built into the training data, but also built into the way we've constructed the internet. Figurative things, such as symbols with double meaning. So a good example of this is you took, the medical help symbology of a staff with two snakes around it, that classic figurative image. If you write poison over it, or something that would be contradictory to Hippocratic Oath, symbols with dual meanings are everywhere. And finally, really, I think the breakthrough, which is going to come, which, if you've studied advanced sort of math thinking, or a lot of the abstract thinking that Einstein was able to do, is always a thought experiment, typically visually driven. And so I think there's a hope that visual reasoning will become a strong aspect of this, particularly when you think about next word prediction. It's complete my sentence, but what if it became more complete my image, which kind of it does exist, or complete my thought? And that really is the ultimate personal assistance, would be that. But clearly, in terms of going from, these are all single imagery, but if you wanted to do video prediction, like what's about to happen next, or write me a movie script, next frame prediction becomes pretty critical. And particularly something like self-driving, where you could use the example of a child driving a tricycle coming out of a driveway. If you look at that frame by frame, you may not be able to predict the child is going to stop. A human is pretty good at that. So this is kind of the break point in which our approach is now BARD versus GPT vision. There's a number of winning examples for BARD, which generally seem to be more about the size of its training data. So for example, I think that engine type is probably because it has Google Images in front of it. And humans have asked in some history that Google has access to. GPT-4 seems to have a number of winning examples in visual logic, and particularly sentiment. I think you could say that's a signature of GPT-4, that it is very kind of safety first, in a way that sentiment becomes an important part of that. So we had the example of anger being misrepresented by BARD and GPT. both models seem to have solved some vision only challenges. So the shape texture thing seems to be maybe back burner a little bit. It seems to have a sort of two-headed version of, if the word doesn't match with the image, we can reconcile it. It still struggles with game position, sequential task, and world knowledge, although I think there's a lot of interest in custom fine-tuning these with physics data. So in conclusion, these models are really designed for what are called the 3 H's. It's the kind of AI constitution. Whatever you do, the model should be helpful, honest, and harmless. And that's kind of, if you have a tough choice in a vision task, honest or helpful are important. So the paper really describes at least 50 image tests. We're focused on vision language synthesis. We did compare 2 large models. BARD does not support image generation per se, but there is a very interesting future, and this kind of shows it in a Lego fashion. You can submit an image to GPT-4, ask it to analyze it, and then it will give you language back, and then you can complete that loop by asking it to create a second image. So in this case, we took a pile of Legos. We said, make a man, draw me a picture of a person sitting in a chair, and then do a 3-section of it falling back in his chair. So this image generation exists really prominently within the latest release of GPT-4. I'm sure BARD will be coming out with it soon. I will say, if you go back even a year ago, doing optical character recognition against tough backgrounds, so like you imagine recognizing words on a non-white background like wood texture, these have gotten very good, and you just have to gasp a little bit about some of the practical applications, like reading, I don't know, pharmaceutical receipts or something like that. One thing that remains obscure, and I can't emphasize enough the challenges of probing this without knowing how the model works. One thing that's a bit obscure is, what are they optimizing towards? Based on what has been published, you can say we have some human safety reviews, some red teams, and they have essentially optimized to be honest, harmless, and helpful. But clearly, you can go to edge cases and test that. And finally, I mentioned you can't get through an AI talk without talking about bias, and whether it triggers you or not, it has a strong English bias, at least in this generation. And so it makes the models vulnerable, and particularly less popular languages or less spoken languages can be manipulated to make models do things that are not helpful, honest, or harmless. So with that, I will turn it back for any answers, and thank you for your attention.